Hey, geometry students. In this lesson, we are going to be talking about a theorem related to the chord lengths of intersecting chords inside a circle. Okay. And here you see, we're just going to start off this lesson with the theorem and the proof of the theorem. So the theorem is this: if two chords intersect in a circle, then the products of the chord segments are equal. So what that means for chord CD, if I multiply the two segments that are part of the same chord, CE times ED, the length of CE times the length of ED. Okay, those two segment lengths, that equals the product of the lengths of the other segment that it intersects, the other chord. So this would be AE times EB. Those products have to be equal. Okay, so the key here is that when you multiply, you're always multiplying the segments of the same chord. So notice I did CE times ED, not CE times EB. That is the common mistake that students sometimes make, is they'll accidentally multiply a segment of one chord times a segment of the other chord, and that's not going to give you the right answer. All right, now how does this work? Like, why is CE times ED equal to AE times EB? Well, there's this really simple paragraph proof that I have here that relates to the similar triangles that are made by two intersecting chords. Okay, so the way we're going to try to prove theorem 86.1, the letters are going to be a little different in our proof. Notice that we did QPT for one chord and RPS for the other. And really, the first thing we need to do is prove that these are similar triangles. We're going to do that using angle-angle similarity. That means that we need to prove that two angles of these two triangles are congruent. And then that means that the third angle has to be congruent because they have to add up to 180 degrees. And then once we have angle-angle similarity established, you'll see that it's really easy then by CPCTC. Actually, no, that's not right. Because remember, CPCTC is for congruent triangles. These are similar triangles, but it's really easy from similarity ratios. That's what we're going to be using, from similarity ratios, to prove that this theorem is correct. All right, so first of all, we start our paragraph proof by saying that we can draw segments QR and ST. And the only reason the only real reason we need for that is that these are endpoints of segments on the circle, and 2 points determine a line. So let's just draw the line segments connecting those 2 points. Okay. Next, we note that they intersect the same arc on the circle. Now, what does that mean? Look at arc RT, and I should really, to name this arc, I should name another point out here because this is the major arc, but I'm just going to draw the arc RT that I'm talking about. It's this one down here. Notice that arc RT is bounded off by the lower 2 points of my chords. If T was way down here, it wouldn't matter. I would still have RT, the arc, bounded off by the two lower points of my chords. Does that make sense? So QT could go here, here, here. It could go anywhere. And regardless of where it goes, as long as they intersect, the bottom 2 points are going to bound off this big arc down here. Now I want you to consider two angles. Consider angle RQT. Notice that when I named that angle, it started with R and ended with T. RQT. And then angle TSR. Notice something about those two angles? Again, I'm going to look RQT, TSR. What are the endpoints of the angle? RT, RT. Because these are these two lower points, and regardless of where they are in the circle, as long as the chords intersect, regardless of where they are on the circle, they bound off this arc down here. Both angles are going to bound off the same amount of arc down here because both have R and T as endpoints. So RQT and RST have R and T as endpoints. Therefore, because they bound off, they intersect the same arc on the circle, they have to have the same angle measure. Okay. So if we have a point somewhere on the circle that's the vertex of an angle, and then the vertex of another angle, but they open to the same arc. They are the same measure. Okay, that's really interesting to point out about intersecting chords. It doesn't matter if like QT went like this and intersected way up here. Like look at this one. Look at ACD and DBA, because they have the same endpoints. Even though you see this one's a little less symmetrical than this one. This one's maybe a little too symmetrical, but DBA and ACD bound off the same arc down here, and therefore these angles have to be congruent if I were to draw these little extra lines in here like we did here. Okay, so that's the first thing you need to recognize. These angles, angle Q and angle S, are congruent angles. And then next, we know that QPR and SPT are congruent because they're vertical angles by the definition of vertical angles. And we know that vertical angles are congruent by the vertical angles theorem. Okay. Hey, I proved that two angles are congruent. Therefore, I can say that these two triangles are similar by angle-angle similarity. And then the corresponding sides of these triangles must be proportional. So we proved that earlier on. That means that I could say RP to PT, okay? These are corresponding sides on similar triangles. RP compares to PT, that's this fraction here, as QP compares to its corresponding side of the triangle, PS. That's this fraction here. And those ratios have to be equal. Well, what can we do with this ratio? What if we just cross multiply? Just like we do when we solve proportion problems. We would get RP times PS. Wait, look at what that is. RP times PS are the two segments of the same arc, equals QP times PT. QP times PT. And we just prove what we were trying to prove based on angle similarity and then just some simple algebra. All right, so now let's use this to solve some problems. Letter A, determine DE. Okay, so we know that, here we go. First of all, we have to read the bold. I missed a step. In circle G, chords A, B, and CD intersect at E. Oh man, it would be really helpful if I drew this one. So I'm going to draw this one out like we always should. Okay, so here's circle G. I'm not going to put a center on the circle, but I'm going to draw A, B, C, D, and I'm going to mark point E, okay? So we're just going to do this. I'm going to make this really asymmetrical to show you that it can be really asymmetrical. Okay, so notice I've got those going for me. I don't know what happened to my circle. That was weird. Let's see. We need to make our circle that color, okay? And then we'll just make sure that this goes all the way to the edge. There we go. And then let's see. Let's put some points on here. We're just going to do points by letters, and we're going to assume that all points are endpoints. So A, B, and C, D intersect at E. We'll make this one A. We'll make, let's see, A. We'll put B right over here. I'm sorry, this would have to be C, because AB is a single segment. So B is the endpoint that has A at the other end. So there we go, B. And then this one up here would be D, and they intersect at E. To visualize these properly, you absolutely need to draw them out. Otherwise, you're not going to be able to visualize where these are 100% of the time. Okay, so now what are we talking about here? Determine DE, this segment, if AE equals 3, BE equals 16. Oh, so I have this drawn wrong, but it doesn't really matter because the rules are still going to hold up. So AE equals 3, BE equals 16. Well, it's going to be 3 times 16 because they're on the same segment. That's 48. And then CE equals 9. What's 48 divided by 9? So it's going to be 48 ninths. That's a really easy fraction. 48 divides by 3, 9 divides by 3. So it's going to be 16 over 3. All right, suppose AE equals 7, BE equals Y, CE equals 4 minus y, and DE equals 2. For this one, we absolutely need to show our work. So this is the letter B, and we're going to have 7 times y, right? Because AE and BE, I need to multiply those, equals 4 minus y times 2. I'm going to distribute this 2 in here, so we get 8 minus 2y, and then I can get rid of my 2 outside parentheses. I can actually just get rid of my parentheses as well. So I add 2y to both sides to get the y on a side by itself. That's going to give me 9y equals 8. Then to get rid of I need to get y entirely by itself, so I'm going to divide both sides by 9. That gives me y equals 8 over 9. 8 over 9. So let's go ahead and check our answer on that one. Y equals 8 over 9. So we had to write and solve the equation. This is the equation that we used. We got y equals 8 over 9. All right, let's look at letter C. In the diagram, LO and PM intersect at N. Find the value of X. Okay, so we have, again, some very simple equation to set up here. It's just going to be 2x plus 4. Okay, I'm going to put that in parentheses and multiply that times 7. So 7 times 2x plus 4 equals 6 times 3x minus 1. First thing we're going to do to solve this is distribute to get rid of my parentheses. So 7 multiplies by 2x and makes it 14x. 7 multiplies by 4 and makes it 28. 6 multiplies by 3x and makes it 18x. And then minus 1 becomes minus 6. Next, I'm going to go ahead and add 6 to both sides. That makes this 34. The other thing that I'm going to do is subtract 14x from both sides. If I subtract 14x from both sides, 18x minus 14x is just 4x. So I get 4x equals 34. I'm going to divide both sides by 4. I'll get x equals 34 over 4, which is 17 over 2. Let's make sure I did that right. X equals 17 over 2. 8.5 is the same thing as 17 over 2. I prefer the improper fraction there.